Alright, so now we're talking about chemical bonding and the three-dimensional structures. So ionic compounds have a crystal structure. We know this, a common ionic compound is salt, and salt, everyone knows, has a very cubic crystal structure, right? So they form so that oppositely charged ions are as close together as possible. So this 3D array of alternating positive and negative ions is called a crystal lattice. So those are some examples of the crystal lattice and the orientations. Again, it all depends on the chemical structure, the chemical formula of that particular compound. So since all the attractive forces in the lattice are the same, you cannot tell them from molecules. Each positive ion is attracted to all of the negative ions around it, and vice versa. So the chemical formula is the lowest whole number ratio for that type of crystal. Again, the whole reason for this is rather than saying this is one giant molecule, which is essentially what it represents, because of the electrostatic nature of these molecules, we're saying, of the ionic compound, we're saying nope, they're not molecules, are actually ionic compounds that have formed this crystalline or this crystal structure. So we're saying that it comes in this lowest whole number ratio. And that it's just like a compilation of this, and that then it forms this structure. So there are many different crystal shapes, and they all depend upon the way the ions pack together. So it depends on this electrostatic pull within the ionic compound, and kind of what crystal structure it is going to form, because it's making these positive ends align with the negative ends. The shape also depends on the relative size of the ions and the charges of the ions. Again, this electrostatic structure. If we look at the structure of molecules, so in a molecular compound, covalent bonds exist between specific pairs of atoms. So these compounds exist as molecules that have a given number of atoms, and therefore they are not necessarily written with the lowest whole number ratio. So a good example of this is our hydrocarbons. Because they form these long molecules, this is what the molecule is. There's no bits that have come to form together to form this molecule. So if we look at VSEPR structure and molecular compounds, the valence shell electron pair repulsion, or VSEPR theory, states that molecules adjust their shape so that their valence electrons are as far away from each other as possible. So, electron pair repulsion is not always equal. It is the greatest between two lone pairs, and less between a lone pair and a bonding pair, okay? And the lowest between two bonding pairs. So the shape is determined around the central atom, okay? So shapes can be classified into 5 categories, and we're going to go into these 5 categories in the next video.